Hello friends, again we are discussing the numericals of hydrodynamic bearing. Before the discussion of numerical on hydrodynamic bearing, we will have a small recap on dimensionless parameters present in a Raimondi and Boyle chart. So in Raimondi and Boyle chart, the various dimensionless parameters are used. First one is a L by D ratio, length to diameter, then HO upon C, minimum oil film thickness to the clearance, then eccentricity ratio. Eccentricity ratio is a epsilon and it is can be calculated as E upon C is equal to 1 minus HO upon C. Then next important parameter is a Sommerfeld number. This Sommerfeld number is again can be calculated as the R upon C bracket square into mu ns upon p, where R is the radius of shaft or journal, C is the clearance between the bearing and journal, mu is the viscosity of lubricating oil, ns is the rps of the corresponding journal, and p is the load per projected area, where p is equal to the w upon L into d. Next one is the R upon C into F, where F is the coefficient of friction. Then we will have a recap on a temperature rise in a hydrodynamic bearing. We know that the temperature is raised due to the heat generation due to the friction power loss due to friction inside the hydrodynamic bearing. We know that the heat is dissipated, what may be the heat generated is dissipated by the lubricating oil. So here what may be the power loss due to friction is considered as a heat generated, and the same heat generated is considered as a heat dissipated by the lubricating oil. So we will calculate the heat generated due to the frictional losses. So first one, frictional torque into angular velocity, which is equal to Fwr upon 10 raised to 3 into 2 pi ns. It will be in watt. So to convert this value into the kilowatt, we have to divide by the 10 raised to 3. So Fwr 2 pi ns divided by 10 raised to 6 kilowatt, that will be heat generated due to friction. So heat dissipated in lubricating oil. The total flow in a lubricating oil is the combination of circumferential flow due to the relative motion of journal and the bearing, and axial flow or side leakage takes place in the bearing. So heat dissipated is equal to heat carried away by the circumferential flow plus heat carried away by the side leakage. So heat dissipated is equal to mc Cp delta T plus ms Cp delta T divided by 2. Now question may arise that here why delta T divided by 2? The major portion of lubricating oil flows in the circumferential direction and is present in the bearing for maximum possible duration. This portion of lubricating oil absorbs the heat during the temperature increase delta T, and the some portion of lubricating oil is constantly leaking from the side, and that is known as an axial flow or side leakage. This axial flow or side leakage is continuous right from the entrance of lubricating oil into the bearing till the exit. Therefore, this portion of lubricating oil is not present in the bearing for maximum duration. So, it is assumed that the axial flow takes place at and average temperature. So average temperature is considered as a delta T divided by 2. Hence the heat carried away by the axial flow is considered by considering delta T divided by 2. So convert these masses into the corresponding flow rate by multiplying the rho, and that will be heat dissipated is equal to rho QCP delta T divided by 10 raised to 9 plus rho QS Cp delta T average temperature means delta T divided by 2 10 raised to 9. But we know that the circumferential flow occurs in a hydrodynamic bearing is the can be calculated as total flow rate minus side leakage. So heat dissipated is accounted as the rho Q minus QS Cp delta T divided by 10 raised to 9 plus rho QS Cp delta T divided by 2 10 raised to 9. So by rearranging the terms, HD heat dissipated is equal to rho Q Cp delta T into 1 minus 1 half of Qs upon Q divided by 10 raised to 9. So by considering heat generated in the hydrodynamic bearing is equal to heat dissipated by lubricating oil from the hydrodynamic bearing. So FWR into 2 pi ns divided by 10 raised to 6 is equal to rho QCP delta T into 1 minus 1 half of Qs upon Q bracket complete 10 raised to 9. By rearranging the terms, we may get the delta T is equal to FWR 2 pi ns divided by rho QCP into 1 minus 1 half of Qs into Q, Qs upon Q into 10 raised to 3, where the Ns is RPS, W is in Newton, rho is in kilogram per meter cube, R is in mm, Q is in mm cube per second, and Cp is in kilojoule per kg per degree Celsius. It is important to note that if the ratio of side leakage to the total flow rate is low, it can be neglected. Now we will discuss this one of the easiest numerical of 360 degree hydrodynamic bearing. This is easiest numerical because all parameters can be calculated from Raimondi and Boyd chart very easily. No any linear interpolation is needed. All calculations are straightforward. So we will discuss this basic numerical. Once you understand this basic numerical, then we will go for the interpolation based numericals. So I am reading this numerical. The following data is given for 360 degree hydrodynamic bearing. Total radial load is 3 kN. Journal bearing diameter is 50 mm. Then bearing length is equal to 50 mm. Journal speed is equal to 1490 rpm. Radial clearance is 50 microns. Then viscosity of lubricating oil, it should be lubricating oil. Viscosity of lubricating oil present in the bearing is equal to 23.4375 centipoise. The density of lubricant is 860 kilogram per meter cube. Specific heat of lubricant is 1.76 kilojoule per kg degree Celsius. Assuming that the total heat generated in the bearing is carried by the total oil flow of the bearing, so calculate first one. So first one is the minimum oil film thickness. Then next one, coefficient of friction, power loss due to friction, total flow rate of lubricant in liter per minute. Please keep in your mind it is in liter per minute. Then side leakage and then temperature rise. Here they didn't mention, it should be by considering or by neglecting a side leakage. So we will consider the both cases, and for that one they provided the Raimondi and Boyle chart for us. It includes L by D ratio HO upon C, then Sommerfeld number R upon C into F, then Q divided by RC NSL and QS divided by Q. So given radial load W, capital W, is equal to 3 kilonewton, which is equal to 3000 Newton. Next one, journal bearing diameter D, small d, is equal to 50 mm. Then bearing length L is equal to 50 mm. So it is L by D ratio. It is clear that L by D ratio is equal to 1. Then journal speed is provided. It is 1490 rpm. So ns is equal to 1490 divided by 60, which is equal to 24.833. Then radial clearance, which is mentioned as a small c, is equal to 50 microns, which is equal to 0.050 mm, 10 raised to minus 3. You can say 50 microns, it can be converted into mm by multiplying 10 raised to minus 3. Then viscosity of lubricating oil present in a bearing, mu, is equal to 23.4375 centipoise, which is equal to 23.4375 into 10 raised to minus 9 Newton second per mm square. Then density of lubricant, rho, is equal to 860 kilogram per meter cube. Then specific heat of lubricant, Cp, is equal to 1.76 kilojoule per kg degree Celsius. So Cp is, so what are provided values? W is provided, D is provided, L is provided. So L by D ratio can be calculated. Ns is provided, small c is provided, mu is provided, rho is provided, Cp is provided. So what we have to find? To find the minimum oil film thickness, means HO, we have to find. Then next one is the coefficient of friction, small f, we have to find. Then next one is the power loss due to friction, so P lost we have to find. Next one, total flow rate of lubricant, means Q, and it should be in liter per minute. Then side leakage, QS, and then delta T, means temperature rise in hydrodynamic bearing lubricating oil, is again a question mark, and for that one the chart is provided. So after reading this given, we can find L by D ratio. So L by D ratio, 50 divided by 50 is 1, and then we will try for the Sommerfeld number. So Sommerfeld number is again R upon C bracket square mu ns upon small p, where this small p is equal to load upon projected area. So W is again given, L and D is again mentioned. So we can calculate this small p, and mu is again mentioned. So we can mu, ns, r, c, all values for Sommerfeld number is given. Hence we can calculate the Sommerfeld number. So calculate the Sommerfeld number. After calculation of this P is equal to load upon projected area, 3000 divided by 15 to 50 is equal to 1.2. Then calculate the Sommerfeld number. R is 50 divided by 2 means 25, and then clearance is provided as a 50 micron, so 50 into 10 raised to minus 3 mm. So 25 divided by 0.05 bracket square, then 23.4375 centipoise is converted into Newton second mm square. So it is 10 raised to minus 9. Ns is already calculated. It is 24.833 divided by 1.2, and which is equal to the 0.121. Now, how to utilize this Raimondi-Boyd chart? For that one, next step is very important. Now we are having first value L by D ratio is 150 divided by 50, and Sommerfeld number we are having as a 0.121. So how to find the solution from Raimondi-Boyd chart? For that one, step number 1, locate the L by D ratio. So we located L by D ratio as 1. Then next one, what parameter we can calculate? So now we can calculate the Sommerfeld number. We already calculated this one, and that we have to locate. After locating this one, we have to locate the Sommerfeld number. So this is the S, and within this column the S is present here. It is present here. So we can say the after locating two values L by D ratio and any another can be calculated, means here in this case yes we are calculated, so Sommerfeld number we calculated. So locate that 2 points. Once the L by D and another parameter is located, that is the row of solution. So locate the row of solution. This is the row of solution. This is the row of solution. So after locating the row of solution, again I am explaining to you. Locate the L by D ratio first. It is 150 divided by 50. We located, and then after this, what will be the calculated parameter? In this case, we calculated the Sommerfeld number. So locate that Sommerfeld number. Yes, into the column of S. Now we located this one. After locating this Sommerfeld number, that is the complete row. This is our row of solution. So for given case, L by D ratio is equal to 1 and S is equal to 0.121. HO upon C is this one. R upon C into F is this one. QRCNSL is this is the value, and QS upon Q is the value. So for this one, HO upon C is the 0.4. Put the value of C, then calculate. So HO is equal to 0.4 into 50 microns, which is equal to 20 microns. Next one is R upon C into F. R upon C into F. From the chart, it is 3.22. Hence, we can calculate the F is equal to. So F is equal to 3.22 into C upon R, and that value is shown in the in this one. Then power loss due to friction, FWR 2 pi ns divided by 10 is to 6, that will be in kilowatt, and put the all values which are calculated by you, and you will get the total power loss due to friction. Similarly, we can calculate or we can find out the QRCNSL from the solution row. This is our solution row. Q upon RCNSL is a 4.33. So we calculated that one. So Q upon RCNSL is equal to 4.33. So Q is equal to 4.33 into RCNSL. Put the all values and you will get the solution of the Q total flow rate present in the hydrodynamic bearing. For hydrodynamic bearing, it is the 67 to 0.52 mm cubes per second. Once the Q calculated in mm cube per second, we have to convert into liter per minute. So to convert this one in liter per minute, we will convert mm cube per second into meter cube per second. So mm cube per second is converted into meter cube per second by multiplying 10 raised to minus 9. So that seconds has to be converted into minutes. So we have to multiply and divide by 60, so that this 60 second will be considered as a minute. So Q is equal to the calculated value 60 into 10 raised to minus 9 meter cube per minute. Then what may be the calculated value into 60 10 raised to minus 9 into 10 raised to 3 liter. We know that 1 meter cube is equal to 10 raised to 3 liter. So the values can be calculated like this. So Q is equal to 0.4032 liter per minute. Similarly, we can calculate the remaining two parameters. Side leakage. So from the row of solution, Qs upon Q was equal to 0.680. So Qs is equal to 0.680 into Q. So Qs is equal to, multiply the corresponding factor, we will get Qs is equal to 0.274 liter per minute. Then temperature rise. We know the formula of temperature rise. Delta T is equal to FWR into 2 pi ns divided by rho Q Cp into bracket 1 minus 1 half of Qs upon Q into 10 raised to 3. Here keep in your mind the Q should be in mm cube per second. Because what may be the derivation we done, that is in mm cube per second. So while calculating delta T, the Q should be in mm cube per second. So with considering the corresponding side leakage, we are getting delta T is equal to 11.22 degrees Celsius. Without considering the side leakage, means Qs is equal to 0, delta T is equal to 7.4 degrees Celsius. So like this way, this numerical can be solved. Here trick is that only how to find the row of solution from the corresponding Raimondi-Boyd chart. If you are having any query, you can contact me on my WhatsApp number. Then thank you. Take care of yourself and your family during this crucial period of COVID-19. Stay home, stay safe. Goodbye.